The third lecture in a series of 5 lectures, and today we will talk about. So this is the plan for lecture 2. We will describe two hard problems, average case hard problems for lattices, called the short integer solutions or SIS problem and the learning with errors or LWE problem. We'll use these problems to construct one-way and collision-resistant hash functions. So this is sort of the mini crypt world of cryptography, one-way functions. Later in lecture 4, I'll tell you how to use LWE to construct public key encryption schemes. And we'll go on in today's lecture, and I'll tell you about a very famous result in lattice-based cryptography, which is ITI's worst case to average case reduction. So informally what this says is that if you can solve these average case problems, if you can solve these two problems, SIS and LWE, on the average, right, you sort of solve it for random instances, then you can solve various lattice problems, let's say the shortest vector problem or problems related to that, on the worst case. Okay, you can solve that for any lattice whatsoever. So that gives a very strong guarantee of security, and I'll try to sort of describe the reduction in its form. Okay, so that's the plan for today. Okay, so let's start off. So what are the cryptographic assumptions that we are all familiar with? Right? The traditional cryptographic assumptions. Factoring, right? Is a canonical cryptographic assumption which says that given a composite number n, find a prime factor, find a prime p that divides discrete logarithm. Says that given g to the power x mod p, find x, find the logarithm, find the discrete logarithm x. Various problems involving bilinear maps on elliptic curves, too numerous to mention, and so all these problems are the number theoretic basis of cryptography. Okay? We know how to build encryption schemes, signature schemes, all kinds of stuff based on these number theoretic problems. Okay, so say I want to go ahead and I want to construct a scheme based on the hardness of factoring. Okay, so how do I go about it? I have to generate a number n that is hard to factor. Okay, I have to generate a random number n that is hard to factor. In other words, I need a distribution on numbers such that if I pick a random number from this distribution, it is hard to factor with all but negligible probability. Okay, the chance that you will end up factoring it, will end up finding a prime factor, is really negligible. Okay, so you need to do that to use factoring for cryptographic applications. Okay, so how do you pick a hard to factor number? Okay, here is a choice. Just pick a random number. Okay, random n-bit number. Is that going to be good for us? Not quite, because a random number is even with probability half, right? So 2 is a factor of such a number, and you're done, right? I mean, it's actually easy to find the prime factor of this number. How would you pick random numbers p and q and let n be the product of p and q? Okay, so that doesn't have this problem, and this is in fact what we normally do in cryptography. But then there are a whole bunch of caveats associated with this process. Okay. In 1978, right after the discovery of Parsec, we discovered attacks on factoring, which mean that the factoring is which means something about the choice of p and q. Okay, so what we need to do is we need to pick p and q such that p minus 1 and q minus 1 have large prime factors. Okay. In fact, p minus 1 and q minus 1 are even, but other than that, they should have only large prime factors. Well, then we discovered that p plus 1 and q plus 1 should have a large prime factor. Well, maybe the largest prime factor of p minus 1 and q minus 1 is p prime and q prime, then p prime minus 1 and q prime minus 1 should have large factors. Wow, I'm not even going to read it. And so on and so forth. Okay. There's so many caveats. So it's not as simple as picking two random primes and setting n to be a product of the two primes. There are so many caveats that one should deal with. So the problem of picking a hard to factor number, a random hard to factor number, is actually a highly non-trivial problem. In other words, What I said is that we need to know a probability distribution over integers, such that picking a random number according to this probability distribution will make n hard to factor. This is what we want to do. Okay. Well, what could we hope? What's the best thing that we could hope, right? Suppose, wishful thinking, okay, suppose that there is a distribution over numbers such that factoring a random number chosen from this distribution is as hard as factoring any number. Okay, in other words, if you had an algorithm that factors a random number from this distribution, you can factor any number that you lay your hands on. Okay, suppose this were actually true. What does this mean? This means that this distribution is actually the hardest possible distribution for factoring. Okay, if you can factor from this distribution, you can factor any number, therefore you can factor from any distribution whatsoever. Okay, if there were such a magic procedure, then I would forget about choosing distributions. I will just pick this distribution because this is really the hardest distribution. Slight catch, which is that we don't know if this is true. This is just wishful thinking. We don't know if there is such a magical, so the hardest possible distribution. Okay, so this is the case with factoring. This is the case with discrete log, and so on and so forth. Okay, so let's look at the problem a bit more closely. There are two notions of hardness. When you talk about hardness, there are two notions of hardness of problem. One is worst case hardness, which says that there are a whole bunch of instances of this problem. So think of these as numbers, right? When I say that a problem is worst case hard, I mean that at least one of the instances is hard, right? Think of sort of NP completeness, NP hardness. When I say that satisfiability is NP hard, what that means is that there is a formula, there is a 3CNF formula for which it is hard to find a satisfying assignment. There could be just one out of a million such assignments, which is hard, but there is one. That's all worst case hardness says. On the other hand, so this is a safe assumption to make, right? I mean, we believe that SAT is NP hard. We believe that P not equals NP, and this is a really sort of safe kind of assumption to make. On the other hand, what we need in cryptography is average case hardness. Namely, we need a problem for which most instances are hard to solve. Okay, so these are the instances of the problem. The red instances are hard to solve instances, and the blue ones are easy to solve. I want most of the instances to be hard to solve. Okay, this is what average case hardness means. And what I said before is that for factoring, we don't know how to relate the worst case and average case hardness. The good thing, in fact, the unique thing about lattices is that for certain lattice problems, there are distributions for which the average case hardness under this distribution is the same as the worst case hardness. Okay? In other words, if you can solve a random instance, you can solve any instance of these lattice problems. Okay? This is a beautiful, beautiful theorem shown by Aitai, 1996. In fact, this is the sort of the theorem that gave birth to lattice-based cryptography. Right. And we will actually see sort of a proof by picture of this theorem later in this talk. Okay, so this is the nice thing about lattices. Lattices, you don't have to worry about picking a distribution, a hard distribution for lattice problems. This theorem gives us a distribution which is actually the hardest possible distribution. Okay, that's a nice thing about it. So a little more details about this theorem. What Aitai shows is he shows how to come up with an average case problem, namely a problem plus a distribution, such that if you can solve the problem on the average for instances chosen according to this distribution, then you can solve lattice problems, say the shortest vector problem that we described yesterday, or related problems on the worst case for any lattice. This is the statement of the theorem. Okay, so what are these average case problems that Aitai comes up with? Okay. Aitai, what he did was he defined a problem called the small integer solutions problem, which I'll describe in a minute, called this SIS. And he used it to construct one-way functions and collision-resistant hash functions. Okay, very basic cryptographic primitives. And later this problem was used to construct digital signatures, identification schemes, and so on and so forth. Okay. that's sort of one average case hard problem on lattices. And what he showed is that if you can solve it, you can sort of go up to the worst case world. You can solve any lattice, the shortest vector problem on any lattice whatsoever. Okay? So that's one problem. It can be used to construct one-way functions, basic cryptographic primitives, really what's called mini-crypt, right? I mean, these are sort of the symmetric cryptographic primitives, so to speak, other than digital signatures. And we have another average case hard problem on lattices called the learning with error problem, which I will describe in the next lecture. And what's good about the learning with errors problem is that it enables you to construct richer cryptographic primitives, namely public key encryption, oblivious transfer, which lets you do secure multi-party computation, right? You can sort of compute any function in a distributed way, keeping privacy of all the parties. Identity-based encryption, hierarchical identity-based encryption, and even fully homomorphic encryption from the last few months. Okay, so this is a very, very powerful average case hard problem on lattices. Okay, so another good thing about these two problems is that you will see in a minute that the description of these problems don't talk about lattices at all. They are purely elementary, linear algebraic problems. And if you want to build crypto systems based on lattices, you can forget about lattices. Well, actually, that's the nice thing about them. You can just work with this nice linear algebraic problem. And what you do is you construct a cryptographic primitive, let's say a one-way function, and you show that if you can break the one-way function, you can solve this problem, SIS, for example, on the average. And then by the worst case to average case connection, you can use that to solve lattice problems. Okay, so ultimately the security of your system is based on lattices. It's based on shortest vectors and lattices, but you don't have to know lattices to construct these schemes. Okay, so that's the nice thing about it. Okay.
Why do you call it mini-crypto?
Mini-crypto. So okay, so anyone says, but so this is a term that Russell Impagliazzo invented. Okay, he divided the world into 5 worlds. Okay. He called it, I might forget all the names, but he called it, what did he call it? Algorithmica, I think. That's the first world. And that's a world where all problems are easy. Okay, factoring is easy, discrete log is easy, all problems are easy. Then there is a world called heuristica. Okay, what is that? These problems are not easy, but there are heuristic algorithms that solve. You can't prove anything about the running time, but they work well in practice. Then there is another world in between, which I forget, which is a strange name. Mini-crypt is a world in which there are one-way functions. There are symmetric key cryptography, but there is no public key cryptography. The public key is sort of one step, beyond it. And cryptomania is really, it's the heaven of cryptography, right? You have public encryption, you have everything. Right? So that's it's just a way to it's funny names to describe various. So again, SIS is a nice problem. It can be used to construct primitives in mini-crypt, sort of basic foundational primitives of cryptography. And LWE is a very strong, very powerful problem. It can be used to construct everything up until fully homomorphic encryption and identity-based encryption. Okay, so let's. Okay, so I said that there is a worst case to average case connection here, in the sense that if you can solve these problems on the average case, you can solve certain lattice problems on the worst case. So what are these certain lattice problems? This is going to be a problem related to the shortest vector problem, but a little bit different. Okay, so this is called the shortest independent vectors problem, which says that which asks the following: given a lattice basis, give me not just one short vector, but n linearly independent short vectors. Okay, so these two are relatively short linearly independent vectors, and these form a solution to the SIVP, shortest independent vectors. And again, like yesterday, we'll not talk about the exact version of the shortest independent vectors problem. We'll talk about the approximate version. So you don't have to give me really the shortest vectors. You can give me vectors that are 5 times this long, and that's fine. So and somewhat short linearly independent vectors. Okay. So a more precise statement of this worst case to average case connection says that if you can solve these problems, you can find an approximate, you can find n vectors which are all somewhat short. You can solve the approximate shortest independent vectors problem. Okay. So that we'll describe that connection later in the talk. But first, let's see how to use these problems to build crypto systems, one-way functions and collisions. Okay. And before that, what is this small integer solutions problem? Okay, so here's the problem. I give you m vectors in ZQ to the n. Okay, so these vectors I represented as column vectors. Okay, each of these vectors is drawn from ZQ to the n, so it has n coordinates, each drawn from ZQ. And I give you many such vectors, m such vectors. So think of m as being much larger than n. Okay, so there are more vectors than the height of the vectors. And what I ask you is this. Find me, okay, so here is the problem. Find me numbers e1 up to em, which are all sort of 0, +1, or -1, such that if I take the linear combination of the AIs with these coefficients, I get a 0. Okay, so find me a subset of with sort of +, -1, and 0 coefficients that sums up to 0, of these AIs that sum up to 0. Okay, so this is really a subset sum kind of problem. Okay. Now, why is this problem hard? What makes this problem hard? Right? Well, let me ask you about a variant of this question, which is, again, I give you a1 up to am, and I ask you to find these numbers e1 up to em, which are not restricted to be, +, -1, 0. You can pick them to be whatever you want, right? Arbitrary numbers in ZQ, such that the sum is 0 mod q. Is this problem easy or hard? Easy. Say that again. How large is q? Q could be anything you want, exponential, polynomial, it doesn't matter. For the version of the shortest integer solution that we use, q will be polynomial. Okay, q will be something like 257. Okay, it's a prime that is a small prime. Okay, so is it easy or hard? I have an easy vote here. Anyone to contradict him? M is polynomial in n, right? N is think of n as 256. M is 1024, okay? Relatively small numbers, right? And Q is 257, let's say. Okay. The point is that if I don't have any restrictions on E1 up to EM, then I can simply use Gaussian elimination. So this is a system of linear equations, right? So how do you solve a system of linear equations? You do Gaussian elimination. That's it. The point is that if you do Gaussian elimination, the solutions that you get are not necessarily small. In fact, with high probability, they will not be small. Okay. So what is hard about this problem is finding a short solution, a short linear combination that sums up to 0. Okay, linear combination with ±1 coefficients. I can actually generalize it. So what is important here is the shortness of the vector E. I can generalize this to saying, E1 up to EM, I don't really care where they come from, as long as the norm, the L2 norm of this vector E is short, small. Okay, this is a generalization which is as hard as this. Okay, this is the problem. Many vectors, find me a short linear combination that sums up to 0. Okay, this is nothing. I mean, this is exactly the same problem, except that I took all these columns, I bunched them up together to a matrix. Okay, so A is a matrix whose columns are A1 up to AM, and I'm supposed to find another vector such that A times E equals 0 mod Q. It's exactly the same problem. Okay, just a compact representation. So, a question that you might ask is, this is a nice problem, right? I mean, how hard is it to describe? So it's a very simple linear algebraic problem. What does it have to do with lattices, right? I mean, there are no lattices in the picture. This problem doesn't talk about lattices at all. So where are lattices here? Lattices are under the hood. I mean, it doesn't come up in the description of the problem, but there are lattices in the picture. And in fact, you can see that the SIS problem is in fact the shortest vector problem on a class of lattices. Okay, why is that the case? Consider the lattice, that creature, never mind what it is, consider the lattice which is the set of all integer vectors, E equals E1 up to EM, right, n-dimensional vectors, such that A times E equals 0 mod Q. Okay, so this is a set of vectors, and I claim that it is a lattice. Okay, why is it a lattice? Because it's discrete. So remember our characterization of lattices from yesterday. Any discrete additive subgroup of z to the m, in fact, is a lattice. So discrete, it's trivial, right, because all the vectors are integers. Additively closed because if I take two vectors, E1 and E2, such that A times E1 is 0 mod Q and A times E2 is 0 mod Q, if I sum them up, that is also in the A times E1 plus E2 is also 0 mod Q. Okay, so this is an additively closed discrete subgroup of Rn, and therefore it's a lattice. Okay, so this is a nice lattice. And what I'm asking, if you think about it, is I'm asking you to find a vector in this lattice, namely a vector E such that A times E equals 0 mod Q, such that this vector is short. Okay, so what is this problem? It's a short vector problem on this particular lattice. Okay. This lattice, this particular type of lattices are called modular lattices. And that's because if you look at all the vectors, all the unit vectors, in fact any integer vector, scaled up by q. So let's say you look at vector q, 0, 0, 0, 0, 0, q, 0, 0, 0, and so on and so forth. They're all in the lattice. Because if I multiply A times E, well, clearly it is 0 mod q. Right? So the lattice is a subset. No, it's the other way around. So this lattice contains all multiples of q, and it is contained in the integer lattice. Okay, so it's lives somewhere between these two sides. Okay, so the containment is actually wrong. I mean, it should be sort of superset of rather than subset. Okay, so SIS is in fact SVP, in fact shortest vector problem. But the good thing is, when you construct crypto systems, you don't have to worry about lattices. You don't have to worry about shortest vectors. Modular lattices. Okay, so once we have this problem, let's go ahead and see how to construct one-way functions from SIS. Right? One-way functions, you know, how many of you don't know? How many of you know one-way functions? Let me see a lot of hands. How many of you don't know one-way functions? I mean, the union should be, you know, the entire set, right? All right. Okay. So in any case, let me just quickly describe what a one-way function is. A one-way function is like taking a glass and throwing it on the ground. Okay. Easy to do, but hard to undo. Right? So that's a one-way function. In mathematical terms, a one-way function is a function that is easy to compute. In polynomial time, you can compute it. But given f of x, it's hard to find any preimage of f of x. Okay. Any x prime such that f of x is equal to f of x prime. Okay, that's a one-way function. What is a collision-resistant function? It is a family of functions. Okay? It's a set of many functions, and the functions are indexed by a key, A, which satisfies two sort of opposing properties, two sort of contradictory properties, apparently contradictory properties. One is that these functions are really hash functions. They're compressing functions. Okay? In the sense that the range of the functions is smaller than the domain of the functions. Okay? So the output length is smaller than the input length. And two, well, of course, if the output length is smaller than the input length, there are collisions, right? There are inputs that map to the same output by pigeonhole principle. And yet, it is actually hard to find these collisions. Okay? So finding two numbers x and y, two different numbers, which map to the same output is a hard problem. So that's what, it has collisions, but it is collision resistant in the sense that it's hard to find these collisions. Okay. This is a collision resistant hash function. Okay. This is a heap hash function. in the sense that for a random function chosen from this family, specified by a random key, it's hard to find collisions because it's a key family function. One can show very easily that collision-resistant hash functions are a stronger primitive than one-way functions. In other words, if there is a collision-resistant hash function, then there is a one-way function. Okay, so I might as well, if I want to construct a one-way function, I might as well forget about it. Might as well construct a collision-resistant hash function. Okay, that's what we're going to do. In fact, you can see that the function defined by taking the key and x and outputting the hash, the key together with the hash of x, is a one-way function. In the sense that if you can invert this function, you can find collisions. So this is the homework. I'm not gonna go through it. Okay. Okay. So that's a collision-resistant hash function. That's a one-way function. How do we construct it based on SIS? Okay. So here is a collision-resistant. Here's a function. I'll claim that it's a collision-resistant hash function. Okay. It's a function that takes whose domain is 0, 1 to the m. Okay. It's all vectors with 0, 1 entries, not -1 plus 1, just +1 and 0 to the m. And the function is defined to be just a subset sum. Okay. The key of this function, the function is keyed by vectors a1 up to am, exactly like in the description of SIS. It takes input z1 up to zm and outputs the subset sum. Okay, that's that. Okay, it's a very simple function. It's very easy to compute. All you need to do is add vector sum. Okay, and I'll claim that this is collision resistant. In fact, it's hard to find collisions. Okay, but before I go there, if this function is not a compressing function, right? Then there might be absolutely no collisions at all, and therefore it is collision resistant. So that's meaningless, right? So we are interested in functions that actually compress. So why does this compress? Not that the domain has size 2 to the m, right? It's all 0, 1 vectors of length m, and the range is a single vector in zq to the m, zq to the n, right? Because I take many vectors in zq to the n, sum them up. Okay. And therefore, the range has size q to the n, and it has sort of n log q bits. To represent it, I need n log q bits. I just said m to be bigger than n log q, which means that the domain is bigger than the range, and I can compress. That's okay. The interesting question is, why is this collision resistant? Okay, why is this collision resistant? What is a collision? Suppose there is an adversary that takes the key of the function a and produces a collision, right? What is a collision? It's two inputs, z1 up to zm and y1 up to ym, different inputs, such that if I apply the hash on these inputs, I get the same output. Right? Let's rewrite it. I get a1 ai times zi minus yi. Sum of these guys is equal to 0. And what are zi minus yi? They are either 1 minus 1 or 0 minus 1 or 1 minus 0. So they're plus minus 1 or 0. Okay, and that's that. I found e1 up to em, not all 0, such that the sum of ai is 0. This is exactly a solution to SIS. Okay, that's that. So this is a collision-resistant hash function from the SIS problem. So this is what we showed. And what I will show in the rest of the talk is the top arrow of this picture. So I showed how to construct a one-way function, a collision-resistant hash function, therefore also a one-way function from the SIS problem. What I want to show is that if you can solve the SIS problem, you can solve the shortest independent vectors problem on any lattice. Okay, so that's yes.
Encryption functions based on SIS.
The encryption functions?
Yeah.
Yeah, it's a great question. So it's a very good question. The answer is yes and no. Yes, because you get one-way functions, right? One-way functions imply symmetric key encryption schemes, secret key encryption schemes, in a very general way. So therefore, there is a symmetric key encryption algorithm from SIS. No, because the only way I know how to construct a symmetric encryption scheme from SIS is to go through this general reduction. So we have this one-way function, which is a very nice one-way function, very simple. Now, once you pass this through this general reduction, things become insanely complicated. Okay? That's the only way I know how to construct a symmetric encryption scheme from SIS. Doing any better is an open problem.
How about public?
Public key, okay. No, we don't know. We don't know. So you can do symmetric encryption, you can do even public key digital signatures, you can do MACs, identification, all from SIS. But once you go to the public key encryption world, you have to, we don't know how to do it. I'm not saying you can't, but we don't know how to do it from SIS. Yeah. It's a good question. So in fact, here's an open problem, right? There is this other very nice cryptographic primitive called a pseudorandom function. Okay? Let's talk about pseudorandom generators. Okay? What is a pseudorandom generator? It's a function that takes a short random string and outputs a long string which looks random. Okay? So it creates entropy out of nothing. Creates computational entropy out of nothing. Okay? So again, pseudorandom generators, you can construct them from one-way functions in a generic way, using this result of Huston in Pagliazzo 11, what they call a Hill theorem. But it's a it's an insane theorem. If you go through this induction, you will get something very complicated. Can you do something better? Can you get a direct, efficient construction of pseudorandom generators from the SIS problem? We don't know. Okay. Okay, good. So this is what we did. And what I want to show is this top arrow, namely that if you can solve the SIS problem on the average, you can solve the shortest independent vector problem on the worst case. Okay. In particular, I want to show a polynomial time reduction that takes as input any n-dimensional lattice, whatever you want, right? It has oracle access to a solver for SIS, so I'm assuming that there is a way to solve the SIS problem. And what this reduction is supposed to do is it's supposed to produce a solution for the SIVP problem. It's supposed to produce n vectors, which are all relatively short. Okay, linearly dependent vectors. Okay, so this was a theorem that originally shown by Aitai, and it was vastly improved by Mikhail Schoenreich. So if you think of the original proof to be about 50 pages, the new proof is 3 slides. Okay, so that's the amount of improvement that Daniela and Odette did to this thing. Okay, so how do you? It's not quite 3 slides. I'm lying to you. It's more like 10. Okay, but so what is the idea of the proof? What do you have? What is your input? Your input is a lattice. It's some basis of a lattice. And the key idea, the key technical idea in the proof is the notion of a Gaussian distribution over lattices. Okay, so the main thing that I will do in this reduction now is that I'll pick a uniformly random lattice point. Okay, so this should raise red flags because a lattice is an infinite object. What does it mean to pick a uniformly random lattice point? We'll deal with it. And I'm going to sample from a Gaussian distribution centered at this lattice point. Now I'll describe all these things in a minute. Okay? So I'm going to pick a random lattice point. I'm going to pick something close to. Pick from a Gaussian distribution centered at this lattice point. Okay? So what is this Gaussian distribution? This is something that we're all familiar with, right? Hopefully. A one-dimensional Gaussian distribution looks like that. So it's a distribution that assigns probability to all the real numbers, right? And it assigns a bigger probability to numbers that are close to 0 and smaller probability to numbers that are far. Okay, so that's something that you're all familiar with. Why talk about one dimensions? What is particular about one dimensions? We don't care. We talk about larger dimensions. Okay, so this is a 2-dimensional Gaussian distribution, which assigns probability to all the points in the plane. Right, the points that are close to the origin get high probability. So this is the kind of the red, the top of the hill, and points that are far away get low probability. particular, the density function of this distribution depends only on the distance. The distance of the point x from the origin. Okay, the normals. This is Gaussian. These are all continuous Gaussian distributions. They have nothing to do with lattices. Okay, they're continuous Gaussians. Now you can also define Gaussians on lattice points. Okay, so you have a lattice. So you can't see it, but they're buried down there. These are lattice points, and I can put a Gaussian on every lattice point. Okay, so each of these hills is a Gaussian distribution, and what this distribution does on any point is the probability density on any point is a sum of the probability densities on all these Gaussian distributions. The sum of these Gaussian distributions. Okay? So, in fact, you have a countably infinite number of Gaussians, and I'm summing them up. So, why should it even converge, right? I mean, it's not clear, but it does. Okay, so it's a well-defined distribution, and this is what it looks like. Okay, so again, Gaussians have this parameterized by standard deviation, right? So standard deviation measures, how spread out the Gaussians. This is a Gaussian with a small standard deviation. As it becomes larger and larger, it becomes more and more spread out. Okay. In fact, here is a Gaussian with a slightly larger standard deviation. Okay. Again, over lattice. Okay, this is nice pictures, right? Fun pictures. Let's do it again. Okay. I increase the standard deviation by a little bit more. This is what I get. In fact, if I keep increasing it, I really get the uniform distribution over the space. Okay. If I take the point is that if I take a large enough Gaussian centered around all lattice points, then it is really the uniform distribution, statistically close to the uniform distribution. Okay. This is a remarkable theorem. I mean, this is the kind of theorem that you think about it and say, gee, this should be obvious, right? Well, let me try to sit down and prove it. It doesn't work. And you think again, and you come up with a very complicated proof. But it's really, but then you think about it again and say, okay, well, this is actually not such a hard theorem to begin. Okay? So this is called it's not a theorem, it's a lemma. It's called the smoothing lemma, which was discovered by Encryption and Draghi. And a little bit more formally, what this says is the following. So a question that might come up is, this is a qualitative theorem, right? So I'm saying if you add a large enough Gaussian, then it becomes, the distribution becomes close to uniform. How large of a Gaussian do you need to add? Right? What this theorem says is that if you add a Gaussian with standard deviation larger than lambda n of L, lambda n is sort of the nth largest vector in the lattice, and then you really get a uniform distribution. Okay? So in the picture before, if you pick the Gaussian to have standard deviation larger than this number lambda n of L times a little fudge factor which determines how close to uniform this distribution is, right? So it has to be something like log n, omega log n, in fact. Then you get uniform distribution. Okay, so this is the main sort of lemma, technical lemma that we will use in this proof. Okay, the proof uses Fourier analysis. I mean, I still haven't figured out why you need Fourier analysis for this, but yes. And an open question is, can you find an elementary proof of this theorem? So the statement of the theorem has nothing to do with Fourier analysis, right? It talks about Gaussians, it talks about lattices. Can you find sort of an elementary proof which doesn't talk about Fourier analysis? Talking about analysis at all, right? And that's I don't know how to do. Okay, so this is the smoothing lemma in any case, and with this, let's jump into the reduction, the worst case reduction. Okay, again, my reduction gets as input a basis of the lattice, some lattice, any lattice that you want, and this is a possibly very long basis. Okay, so if I had a short basis, well, then I have many short linearly independent vectors, so it's pointless, right? So this basis is a very long basis. Doesn't look like in the picture. This is actually the shortest basis of this lattice, but this is the limitation of 2 dimensions. Right? Okay, so that's what I get as input, and what do I want to do? Right. So I have at my disposal an oracle that solves the SIS problem. Okay? So what I want to show is that that oracle helps me to find many short linearly independent vectors in the lattice. So how do I use this oracle? Okay, I have to generate inputs to this oracle. How do I do this? Here's the way. Okay. Let me take this lattice and let me divide it. Okay. So let's say the modulus is 3. Okay, it's not like 257, it's 3. So what I'm going to do is I'm going to divide the lattice in each direction into 3 parts. Okay, I'm going to divide the parallelepiped into 3 and so on and so forth. Okay, so the parallelepiped now has 3 times 3 equals 9 subdivisions. And I'm going to number all these guys, 0, 1, 2, 0, 1, 2, and so on and so forth. Okay, infinitely in each direction. Okay, so now, okay, good. So the one thing to note about this numbering is that all lattice points have label 0, 0. In n dimensions, it's the all zeros vector. And the points inside the parallelepiped have, non-zero numbers, non-zero labels. Okay, so like, we built up all this sort of stuff about Gaussians, presumably to help us in this proof, right? So here's where we are going to use it. We're going to do the following. So we're going to pick a random lattice point. Okay, I haven't told you what is a random lattice point. Think about picking a random lattice point within a large, huge grid. Okay, this I can do. I'm gonna, once I have a lattice point, which is a red point out there, I'm going to sample from a Gaussian surrounding this lattice point. Okay, so that's the yellow point out there. So, good. Okay, pick a lattice point, sample from a Gaussian around this lattice point, I get the yellow point. I do this a bunch of times, not just one time, m times. Okay, and what do I get from every sample, from every yellow point that I picked? I can construct a vector AI, right? So, what is this vector? Do I have? Okay, well, let's just look at the picture. Okay, so let's look at the leftmost yellow point. Okay, what is its label? It is 1 on the x-axis and 1 on the y-axis. Okay, so it's 1, 1. And the second guy is 2, 2, and this is 0, 1. Okay, so these are the points that I sampled. So these are n-dimensional vectors. Okay, m vectors each live in n dimensions. N is 2 here, right? And that is actually a kosher input. That's a nice input to the SIS oracle. Okay, so I have an SIS oracle at my hand. I give it, a1 up to am. I ask for, a short integer solution to this instance. Okay, so that's how I'm going to use the SIS oracle. Okay, so why is this good? So why should the SIS oracle even work on this instance, right? So what is the SIS oracle supposed to do? If I give it random vectors, a1 up to am, then it will give me a linear combination that sums to 0. Okay, I created some vectors, a1 up to am. Well, why is it supposed to be random? So that's exactly where we use the smoothing lemma. Okay, so if I pick this Gaussian to be large enough, then these labels, the labels that I get for these vectors are in fact random. Okay, so what I feed to the SIS oracle is in fact m random vectors in ZQ to the n. So the oracle cannot top out, right? It has to give me a solution now because I gave it a legal instance. Okay, so give these things to the SIS oracle. What does the oracle give me? It tells me a linear combination of a1 up to am with plus minus 1 and 0 coefficients, which sums to 0, 1, q. Okay, so it gives me a solution. That's great. And now, the ball's in my court, right? I have the solution. I want to use this to find a short vector in the lattice. Okay, so far, everyone's with me? Good. How do I do this? Okay, let us look at these vectors. Look at these vectors that I sampled. The red vector, I'll call it vi, right? v1 up to v n m. And the Gaussian sample, I'll call it si. Okay, so Vi minus Si is actually a relatively short vector. In fact, one of length really lambda n of L, right? Because a Gaussian had standard deviation roughly lambda n. If I sample from it, I'll get a vector of length lambda n times square root n, perhaps. So the point is that the Ri is actually very short. Okay. Now let's look at what the SIS oracle gives us. It tells us that the sum of AI EI is 0 mod q. Okay. What that means is that if I take all these yellow points and sum them up using the same coefficients, I will get a lattice point. Okay, so the AI, remember, they are the labels of the yellow points. Okay, so they are 0, 0, 1, 1, and so on and so forth. If I sum them up, I will get label 0, 0 mod q. Right? Let's go back to the Gaussians. What that means is that if I take the same linear combination of the Gaussian points, I will get a point with label 0, 0. But what is a point with label 0, 0? It's a lattice point. Okay, so what this oracle gives me is a lattice vector. Okay. Okay. Well, what is SI? It's Vi plus Ri, right? That is, I just rewrote things. That's also a lattice vector. Let me split them up. So it's the sum of Vi EI plus the sum of Ri EI. That's also a lattice vector. Same. I mean, I didn't do anything. I'm just, doing trivial manipulations on these quantities. So now, the sum of, what are the VIs? Okay, the V1 up to Vm are lattice points. Okay, so a linear combination of lattice points is also a lattice point. So this guy is a lattice point, and the sum of these two guys is also a lattice point. So the difference, namely the sum of Ri, R1E1 plus up to Rm Em, that's also a lattice point. Okay, there's a difference between two lattice points. Now, I claim that we are done. Almost. Okay, so why is that the case? So you get this lattice vector, and I want to claim that this is actually a short lattice vector. Okay, why is that the case? Because Ri, the distance between Vi and Ei, it's really the standard deviation of the Gaussian, which is small, right? And the Ei are plus minus 1, 0. So I take a short linear combination of short vectors, I get a short vector. It's going to be a little bit longer than before, but it's still a relatively short vector. So quantitatively, so this is a short lattice vector. Quantitatively, what do I mean? Well, the length of the Ri's is roughly the standard deviation of the Gaussian, which is lambda n, right? I mean, that's what I need to get the smoothing lemma to work, times square root n, because if I sample from a Gaussian of standard deviation, 100, the vector that I get has length 100 times square root n with high probability. Okay. So this is the length of the Ri's. So now I'm going to sum up m of these guys with plus minus 1 coefficients. So just let's do, let's invoke, what is it called? The center limit theorem, right? Sum of Gaussians is also a Gaussian with standard deviation square root m times the original standard deviation. Okay, so square root of n times lambda. That's the length of this vector that I get at the end, which is roughly n times lambda. So what I get is a vector that's at most n times the nth shortest vector of the lattice, n times lambda. Okay, so I got one vector. Okay, but I'm supposed to get many vectors now. How do I get many vectors? Just do this process again and again. Okay, restart. I will get another vector. Keep doing it again and again. Eventually, it needs some arguing, but you will get many linearly independent vectors, all of length at most n times lambda. Okay, and that's that.
Sorry, what is lambda n?
Lambda n is the nth largest, the length of the nth largest vector in the lattice.
Oh.
Right. So, say that again. What is n? N is the dimension. N is 2. Here, n is the dimension of the lattice. Okay. So what we called m yesterday. Okay, good. So m became n today. So it went to sleep, woke up, it found out that it's n. So.
Okay, well, would you explain the first line, the dome of Ri is
Good. So So what is Ri, right? Ri by definition over there is Vi minus Si, right? So I picked a lattice point, I added a Gaussian, so it's really the length of the Gaussian vector that I sampled, right? And how large does this Gaussian have to be? Well, it has to be large enough to apply the smoothing lemma, right? So large enough so that the distribution is kind of uniform, right? And so the smoothing lemma says that this number is really lambda n, the lattice, the length of the nth longest vector of the lattice. Okay, so in other words, the smoothing lemma, what it says is that if I add a Gaussian with standard deviation lambda n, then I get a uniform distribution of space. So let me describe this a little bit more. So why does this lambda n number make sense? Right? Okay, so consider this lattice. Okay, you know this terrible lattice. Right? So it's lambda 1. So this is 1 0, and this is 0 1,000. Let's say. Okay, the shortest vector, the length of the shortest vector is 1. Right? So the lambda 1 of this lattice is 1, and lambda 2 of this lattice is really the length of the second longest vector, which is 100. Right? So now the question I want to ask is, I want to do the following experiment. I want to pick a point from Gaussian distributions centered around all lattice points. Okay, so that's the experiment that we have. Pick a random lattice point and pick a Gaussian sort of point surrounding this lattice point. And what I want is that if I take the union of all these spheres, so Gaussian is like a sphere, right? I mean, it's more or less so the interior of a sphere. And what I want is that if I take the union of all these spheres, it should really cover the entire space. In fact, I need something more than that, but I need at least the fact that it should cover the entire space, right? So how large should this sphere be? Like at the minimum, how large should it? Can't be 1, because then it will cover, you know, this, but not this. There is a huge amount of open space between these two. In fact, you can see that it has to be at least as large as lambda n over 2, 50 in this picture. Right, so I have to pick a Gaussian with the radius at least lambda n over 2 to even be able to cover the entire space. Right? And what the smoothing lemma says is that this is actually tight. If you pick from this Gaussian, you will cover the entire space. In fact, you will cover sort of the entire space in a smooth way. Namely, you know, each point sort of appears in the same number of spheres, more or less. Okay, so that's why the lambda n is important. I mean, the standard, I have to pick from a Gaussian with standard deviation lambda n, or more than that. More is fine. And now, when I pick from this Gaussian of standard deviation sigma in n dimensions, the vector has length sigma times square root n, right? So each sort of coordinate is roughly sigma. And so if I take the L2 norm of this vector is square root of sigma squared and so forth, then sigma times root n. Right? So that's why that number is important. The second line says that I'm going to take a linear combination of these Ri's, each of length that much. Right? So I'm going to take a linear combination of many Gaussian vectors, m Gaussian vectors, and I know that if I do that, I get a Gaussian of standard deviation square root m times the original standard deviation. Okay? And that gives you, so it's square root m times the this number. Okay. So forget about if you want to do it, forget about the quantitative aspects of this theorem. What this says is that you get a relatively short vector. What do I mean by relatively short? Its length is polynomial factor away from lambda n, the lattice. Okay, the nth longest vector, nth shortest vector of the lattice. Okay, and this is exactly what we wanted to find. We wanted to find many vectors, each of whose length is at most lambda n.
it doesn't matter how large Q you take here.
Ah, good. That's an excellent question. Excellent question. So far in this calculations, Q didn't come into the picture at all, right? I mean, I didn't even talk about it. Q was 3, in fact. So why is Q important? Right? You'll see in a minute. Okay. So in fact, it's probably even the next slide. Oh, good. Okay. So there are a number of things that I slipped under the rug in this proof. Well, first of all, you can't sample a uniformly random lattice point. I mean, it's an infinite set. You know, the notion isn't even well defined. And what we will do to take care of this technicality is that in the proofs we'll work with Rn modulo L, the space Rn modulo L, which is really saying that I will forget about this infinite space, and I'll only look at the parallelepiped, so the fundamental parallelepiped of the lattice, right? Because everything that happens outside is really a copy of what happens inside the parallelepiped. Okay, so I can restrict my attention to this sort of bounded region. So that, in fact, can be taken care of, which means that you don't have to deal with this sort of annoying issue of what the random lattice point means. Okay, so the second question is, well, what did I show you? I showed you that I showed you a vector, a lattice vector, right, which is short. But it's easy to find a short lattice vector, right? I mean, 0 is a short lattice vector. So I have to show you that this is actually a non-trivial lattice vector. In fact, this is not equal to 0. So that can actually be shown. That can actually be shown using sort of an information theoretic argument. So I'm not gonna show it. Okay. And finally, we come to Junki's question, which is, why is this modulus? Where does this modulus come into the picture? Okay. So this is another place where I cheated, which is this, right? So I said, take a lattice point and sample from a Gaussian surrounding the lattice point, and I magically assumed that when I do that, the point will fall on this grid, on this subdivision of the grid. Why would that happen at all? Right? You see the point? I take this point, I sample from this continuous Gaussian surrounding this point, and I assumed that the resulting yellow point will fall on this subdivision. There's no way that's going to happen. Right? Absolutely no way that's going to happen. So what we do is we have to take care of this issue, which is that what you do when you sample is you get an arbitrary point, which doesn't necessarily fall in this subgrid, but you round it to the closest point in this smaller grid. Okay, and then you work with that point. So what happens when you do that is that it introduces a rounding error. So the lattice vector that you get at the end will not be as short as before. It will be a little bit longer, so the length depends on the rounding error. Okay, and here is where Q is actually important. Okay, so if you have a very small Q, let's say Q equals 3, right? Then the rounding error can actually be very big, right? Because I could have a lattice point that lies sort of in the middle of here, and then when I round it, I'm essentially adding a huge vector. So the vector that I get at the end, the lattice vector that I get at the end, will not be as short because I have to compensate for this. That's why I have to use a large enough modulus. So I have to divide it in a fine way, so that now I sample it, I have to round only a little bit to get it to the subgrid. Okay, that's why it's important to. In fact, this theorem doesn't work for all moduli. It only works for modulus Q that is larger than n, which again comes in because of this rounding error. Okay, that's another what I call technicality. It's an interesting technicality, but to understand the part of the proof, you don't have to. Okay, so that is the proof. That's the proof of the worst case to average case reduction. and I'm done with this part of the talk, which is actually it's twice as fast as I imagined. So what if we take a little break and we restart?
So I guess we'll have a